So, hey everyone, welcome to the Multimodal Weekly webinar series hosted by the team over here at 12 Labs. We've been meeting every Friday at 1:30 p.m. Pacific time over the past almost 4 months. Some of you are new here for the first time. Some of you been joining the series regularly. So here are some of the topics that we tend to cover on a weekly basis. Newest research in multimodal AI and foundation models, innovative multimodal application in different verticals. Since Charlie focused more on video studying, sometimes we also have folks talk about video AI and multimodal projects that they like to share, core video infrastructure technologies, and occasionally we have team members from 12 Labs give tutorials and guides on how to use our solution. In the past session, we have a wide variety of speakers, from researchers talking about multimodal large language model and LLMs stuff to one like practitioner talking about retrieval augmented generation and open source multimedia amplification content. And we also have to startup founders talking about a variety of projects they're working on related to video synchronization and video storyboarding. So for this session, we have two speakers. The first one is Minjoon Seo, who's currently an assistant professor at the Korea Advanced Institute of Technology, and he's also a chief scientist here at 12 Labs. And he will give a talk about the research work that he and his team over at the university working on called FLASK, fine-grained language model evaluation based on alignment skill set. So definitely very interested to hear more about different evaluation paradigm, right, for evaluating the quality of these models that are coming out on a very rapid-based basis. And the second speaker is Tahreem Rasul, currently a senior machine engineer at RedBuffer. I got introduced to Tahreem by Nahid, who is one of our previous speakers at the webinar. And Tahreem will be able to talk about medical visual question answering, especially on how you can leverage multimodal insights when you work with medical data. And we have a couple of folks in our community who are deep into healthcare AI. So it would be super cool to hear Tahreem's perspective on specific technical challenges and potential solution to tackle some of those challenges. So here's some quick logistic note. Feel free to send your question on the Zoom chat. Ask the speaker, give talks, and they can navigate to this question after they finish. And we'll also have a short Q&A session, probably 5 minutes towards the end, one word on finish. So with that introduction out of the way, I stop sharing my screen, and Minjoon, do you want to get started?
Yeah, thank you for the introduction. Let me see if I can share the screen. Okay, works. All right, so as James introduced, today I'll be talking about our recent work, well, from the university side, which is evaluation protocol for large language models. So first, let me get to motivation and brief introduction of the work. So we apparently know, especially since the introduction of Llama and open source of Llama, there are a lot of large language models coming out these days. I think I started with Alpaca and Vicuna in early March this year, and now I think there are countless number of language models that I think just come out every day, every week. And actually, we are also working on some of the language models, fine-tuning these Llama or open source language models. And we actually also released one of back then quite good accuracy model. But we actually realized that after evaluating our own model that we developed back then in, I think, May-ish, June, we found that the evaluation process that people use a lot is somewhat broken. So apparently, like for instance, if you look at these Hugging Face leaderboard or Alpaca eval leaderboard, I think they're of course serving great purpose of having a rough sense of how good these language models are. But as you see, well, these quantitative results that we see, especially for instance, like leaderboard that just use one score, or there's like win rates between, for instance, two models. It is actually the result that they show on the leaderboard is oftentimes quite different from the qualitative user experience that we actually feel. And we thought that this is actually not a good thing, because I mean, what we really care about is at the end, we want the large language models to actually satisfy the customer needs, the user needs, and also they actually feel that the language model is quite smart. But then it was not always the case. Even if the average score is quite high of a certain language model, it doesn't necessarily mean that the language model is better than the other. Sometimes it's almost indistinguishable. So that's actually where we're thinking about creating a better, or I would say, we cannot say our evaluation protocol is the best protocol, but we wanted to actually look at the evaluation from a different perspective. So I think essentially we are actually believing that we are a believer of more of we need different various evaluations to correctly understand how good a language model is. So we don't think there is a one single evaluation protocol that just fits to all needs. So I think it would be good if you can think of this as like one perspective that we had, and one perspective that I think is quite helpful to understand language models in a more unbiased manner. Yeah, so again, if you look at these different benchmarks, so there are like automatic metrics like MMLU, BBH, Bespeak Benchmark, and Open Language Model leaderboard from Hugging Face. And there are also non-automatic, more of a preference-based evaluation, whether it's human-based or GPT-4-based. So they basically ask these good, very Oracle language models, like, I mean, really good language models, like state-of-the-art language models like GPT-4 or humans, and then ask them to compare between two model results like Vicuna, Chatbot, Arena, and Alpaca eval. And each has some pros, right? Like for instance, automatic one is very comprehensive, and the preference-based is quite scalable, because if you're using GPT-4, then you can do it quite fast. But then they also have cons, right? The automatic ones is not really scalable, and it's not reliable, because in many cases you're actually trying to just classify whether an answer is correct or wrong. But then if you're talking about long form answers, then they're apparently also not interpretable so much. Because it's not about qualitative aspect of the response, it's more about whether it's correct answer or wrong answer. And preference-based also has some disadvantages. There are limitations. They're not really comprehensive, because they're actually looking into just a few cases. It's not reliable because it has also bias. The GPT-4 has a lot of bias. And it lacks interpretability as well. It has a bit more interpretability than the automatic one, but still it lacks it. So that's where we were trying to design our new evaluation protocol, which is called FLASK. So actually, the key idea here is actually we want to be more fine-grained, and that actually makes the language model less biased. I mean, the evaluation language model less biased. And also it makes the evaluation more, I would say, accurate in many cases. And when we're trying to make this fine-grained, the central idea that we wanted to promote is the skill set, the concept of a notion of skill set, where we're assuming that each task, each question requires a set of skills to answer that question. And that means different questions have different skill sets, and we wanted to annotate these skill sets up to 3 per question or per instruction, so that we can actually diversify different skill sets with among the given questions, which are actually collected from the existing data sets mostly, but we had to annotate manually, so expert annotation from actual researchers, so that we have enough instructions and also enough skill sets annotated. So, for instance, then at the end, what we wanted to see is something like this. It's actual result, actually, but so we wanted to compare different language models with different aspects. Like, for instance, we're seeing here Vicuna, Alpaca, Llama 2 Chat. I think these are well-known, state-of-the-art open source language models. Of course, they're fine-tuned on instructions. They're not the original foundation model. And we have some, I think, seemingly similar proprietary language models like GPT 3.5, BARD, and Claude. And I think GPT-4 right now, everyone probably agrees that it's best among all the language models. So then, as you see, we can have a more comprehensive comparison between language models. And as you see, Alpaca is overall doing the worst, and Vicuna and Alpaca 13, the Llama are, I think, relatively similar, but still, I think in this case, Llama is a bit better. Llama 2 Chat. And proprietary language models have a even more gap, and we see GPT-4 is doing better. So let's get into each skill set. I mean, in more details, including the skill sets. So we have 1,740 overall queries. These were actually collected from 122 existing NLP datasets, but we actually manually picked these and also manually annotated the required information to evaluate. So the steps go as follows. So step one, we first actually do metadata annotation. So we want to classify what the domain of each question or instruction is. So when you see instruction, you can think of this as a question, and also annotates skill sets required to answer the question or the instruction, and we just choose top 3, even if there are more than 3. And also we label difficulty, whether it's easy, medium, or hard. And actually, it's actually probably we did more fine-grained difficulty, but you can think of it as 1 being really easy, 5 being really hard. We also did scoring process, so we score each skill in a range of 1 to 5. So then at the end, well, the domain we can classify these questions into following domains: culture, humanities, social science, technology, language, math, coding, natural science, health, and history. We see some of the questions, some of the domains have less questions than the others. And we divide the skill set into 4 core areas: logical thinking, problem handling, background knowledge, and user alignment. So logical thinking usually involves logical robustness, logical correctness, logical efficiency. Basically, you're asked to do something that's very reasoning and logical, and we want to evaluate that into 3 aspects. And problem handling goes more into whether the model is able to really handle the problem well. So it deals with insightfulness, completeness, metacognition, comprehension. We have more details about what we really think about these things are. And in the background knowledge, we have factuality, which means, of course, whether the answers are factual, and common sense understanding really deals with relatively, maybe it's not really, it's factual, but it's something that everyone just knows, because it's common sense, right? And user alignment really deals with whether the answers are concise, they're harmless, and also it's readable. And actually, we have referred a lot to this previous paper by Anna et al., where they actually outline the taxonomy for NLP resources. And we're not using exactly the same terms from them, but our work was largely influenced by this paper in terms of taxonomy. And again, difficulty level is quite simple. I mean, it's 1 to 5, whether it's simple or it's expert level. And actually, we're referring to this work. So for instance, let's say that we have a question like solve x squared plus 2x plus 1 equal to 0. You can ask this to your favorite language model, right? And then we hand label this to be domain to be math, or we sometimes use language models output, like GPT-4's output, if we think it's reliable. And we label that to be, actually we use the GPT-4 for many of the questions, but we actually had to hand label some of them so that we can give some future learning, in context future learning. Skill set is logical correctness, comprehension, and logical efficiency, right? It's quite clear why it deals with two logical things, and comprehension is whether, in this case, the user understood the question correctly. And difficulties, probably it's quite easy. Like I think any middle school or high school student can solve this. So let's say that we have three models, right? Model A solves like x squared plus 2x plus 1 equal to x plus 1 squared equals 0. And the square is always greater than or equal to 0. So x plus 1 equal to 0. And model B says x squared plus 2x plus 1 equal to x minus 1 square 2. You see where something got wrong. So x equal to 1, which is apparently wrong. X squared, well, C is they actually do this wrong. X minus 1 squared. It's not x minus 1 squared 2, right? But actually are able to retrieve the x plus 1 again. So it's quite weird, of course, but language models do that sometimes. So actually the final answer is correct. And in that sense, then logical correctness here, model A is 5. It's perfect, right? Nothing's wrong. Comprehension is 5, and logical efficiency is 5. Easy, right? But if you look at the model B, correctness is 1 because the answer was wrong. But it seems like the user at least understood. I mean, not user. I mean, the model B's understood how to solve the problem or what the question is about. So comprehension was not too low. It was about 4, and logical efficiency was also quite high because the only place that the model B got wrong is this minus sign, but the solution is quite concise, right? Whereas model C, the correctness is 5, comprehension is also 5 because it looks like model C correctly understood the question, but the path to the final answer was quite long. So that's why efficiency is 2. So that's what we do, basically what FLASK does. So if you go through these steps, then you can see that, well, how much our data set, well, what's the breakdown of the FLASK data set? So you see that a lot of questions actually deal with comprehension and common sense and factuality, but we have quite non-trivial number of other questions in other skill sets, and you can also see that the domain is quite spread out too. And difficulty also is quite spread out, except for level 5, which is relatively few, only 170. And actually, when we saw that, as you saw previously, proprietary language models do quite well overall on FLASK, right? But we wanted to open source language models still struggle with FLASK, but proprietary language models are quite good at FLASK overall. So we wanted to also make a hard version of FLASK, which we call FLASK hard. So these are the among the FLASK questions we saw there were 170 questions which are level 5 difficulty, and among those there were about half of them had ground truth answers. So basically, because we're getting these questions from the actual NLP data sets, in many cases they don't have ground truth answers. I mean, the long form answers, they might have short form answers, but not long form answers. So we just chose about half of them that have ground truth answers, which we call FLASK hard. So these are deemed to be very hard questions. So if you look at the FLASK hard, we see that language models struggle a lot. So when you look at the entire FLASK, it's like this, but then you see that these shrink a lot with the FLASK hard. So I think I went over all the important details, but happy to answer any questions. I have a few more slides, but I think just given my time limits, I think it would be good to have some questions, and if not, then maybe I can just go to slides, of course.
Yeah, is there any question right now for Minjoon? If not, then we can finish some of the remaining slide and we can dive a bit deeper.
Yeah, actually, I would like to ask a question. So first of all, thanks for sharing your work. I'm curious, you mentioned at the beginning that one of the goals was to reduce bias. Can you be a little bit more specific? Because I mean, bias is such a broad term, and I always struggle to understand
Okay.
what specifically people mean, because like as I was saying during one of our previous call, it seems that everyone wants to be represented equally, but obviously is going to be impossible. So I'm curious to know your perspective.
Good question. Yeah. So when I say bias, of course, bias has, I think, it could have different meanings, but I think one example is something like this. So suppose that let's say we're considering this alpaca eval leaderboard, and what it does is basically you want to compare two language models accuracy, or basically you want to compare between them and then see which one wins. So when it says Llama 2 Chat 7db wins 93% times, which it means then when it's actually fought against other models, then it's winning 93%, right? From the, of course, GPT-4's perspective. So GPT-4 is the one that actually evaluates which one won. So GPT-4 is actually also both player and evaluator here.
Yeah.
And the problem is that evaluator has a bias, means evaluator is looking for certain, for instance, keywords. And when it sees such keywords, for instance, or a certain way of saying things, the evaluator has tendency to give higher score to that language model. So basically, it's exactly biased towards the language models that say in that way. So for instance, maybe GPT-4 might give higher score when the language model says something like a very like trivial statement, something like say, for instance, it can be inferred that blah, blah, blah. So maybe GPT-4 thinks that when that such sentence appears and it has a more credibility than a model doesn't say it can be inferred that. So I'm not saying that it's as simple as that, the biases. I mean, bias can be more subtle things. But what I mean by is that you can tune your answer, how the model says the answer differently, and the GPT-4's evaluation could be quite widely different. It could be going from, for instance, score of 5 to maybe score of 3, just because you actually didn't say that, or you actually said something that's not good. So I think that's like one kind of bias, language models output, but also it has some bias towards what kind of prompt you give to GPT-4 to evaluate. So for instance, you might ask which model's output is better. Then you might say, oh, Llama 2 is better than OpenChat. But then if you ask the model to if you ask GPT-4 to actually evaluate, for instance, score each model separately, and then if you compare the scores at the end, then you might actually see that OpenChat is winning instead of Llama. So depending on how you ask the GPT-4 to evaluate the model, the which model wins could be changing. So that's I think very I'll say not everything, but I think the most frequent cases of such bias of language models when evaluating.
Right.
Okay, thanks.
Yeah, thanks for asking, Mario. There's like 3 separate questions in the chat.
Okay.
Maybe we can go over like at least one of them, and then if Minjoon, if you can answer like the other 2 asynchronously,
Sure.
could be great.
Okay, I'll probably try to be quick.
Just choose the one you wanna answer.
Okay, yeah, I think I can go through all of them. I know 2 or 3 minutes hopefully. So first of all, Tony's question. Yeah, evaluation process actually mostly is done in GPT-4. Sorry, I actually didn't mention that. So evaluation process is mostly done in GPT-4. Some of them are actually done manually through humans. Of course, the reason is that it's much more expensive with humans. And is there any kind of priority between different metrics like correctness or efficiency? So if you're asking about whether any one of them has higher importance than the other, no, actually, in our evaluation setup, we actually do not try to average them because that's exactly without defeating the purpose of having fine-grained evaluation. But I think as you see, there are some metrics that all models do really badly. So I think those are probably will be priority for developers. Next question is, how does the scoring process function on expert evaluator side? For long form output is consequence or negative points given for hallucinations. Okay, so you're saying the expert evaluators are you talking about GPT-4 or here are you talking about the difficult questions? Oh, GPT-4. Okay. I think the short answer is that basically we want the GPT-4 to answer to evaluate the response, but in a more fine-grained manner. So it's not just asking GPT-4 to yeah. So I think the key here is that we want the GPT-4 to score each in a fine-grained manner, meaning it's not like just asking GPT-4 to, okay, what's the how good this output is, but more of a, if we break down the questions criteria, just like actually how we are using rubric when we're answering questions. I mean, evaluating for instance exams, right? We have very detailed rubric to actually make this score fine-grained. So I think one of the findings that we wanted to really emphasize is that being fine-grained is quite important, which might have been obvious for humans, and maybe it's not too surprising that models are similar similar too, but fine-grainedness actually increases robustness and reliability, and of course they will give better scores for hallucinations too. Yeah, I'll go to the next question. Thank you for can you explain how and if we could design autonomous agents using this FLASK evaluation process? Yeah, so I think probably if you're creating autonomous agents that are not just about answering questions, but really about doing something else, then I think my suggestion is that probably you cannot use FLASK directly for your use case, but it's more of a, I think the key takeaway here is that when you're evaluating your system, you should avoid from just asking GPT-4 how good it is. You should try to really have a very detailed prompts about what you want to evaluate, a very step-by-step, just like how you would ask humans to evaluate when you want the grade to be very precise, right? So it's basically creating rubrics. So I think that's the key takeaway. So probably you cannot use FLASK directly, but you can borrow some ideas from, I think, our paper and try to apply that to your use case. I think, so, yeah,
I think that's great. Yeah, I'm sure there's might be like a lot of other questions given the density of the information being presented. And if you have any of them, feel free to put in the chat. But yeah, let's move on to Tahreem, so we can get started with a presentation.
Yep. All right. Thanks.
Minjoon. Yep.
Yeah, I think I'll just share my screen and then we can just get started.
Yep.
Okay. Yeah, so should be visible. Yeah.
That's good.
Great. So today, hello everyone. So yeah, I'll try to keep this short so that you guys don't get bored. But today we'll be talking about medical visual question answering. I think James did a nice intro. So we'd be seeing how we can leverage multimodal insights for medical imaging analysis. And I'll start with a brief introduction of myself. I'm currently working as a senior ML engineer at RedBuffer. We are a services-based ML and AI company. Prior to this, I worked as a medical physicist for cancer radiotherapy research at Siemens in Erlangen. That's also where I did my master's in medical AI from, and my bachelor's or my background is in electrical engineering from Islamabad, and that's also where I'm from. And I think with that we can just start with yeah, the topic. So okay, so I'd like to sort of briefly introduce the domain for somebody who is not familiar. So visual question answering in very simple terms talks about a computer that can describe an image. And basically we're merging the domains of computer vision and natural language processing here. And in recent times, there has been a surge, right, in adapting VQA to the medical field. And this, I think, can be attributed to a bunch of different reasons. But one of them is that it promises to help doctors in decision making and diagnoses. So medical VQA stands out really because it can handle any question, or that's at least that's the promise. That it can handle any question in plain language and respond to questions that you ask the pipeline. So let's imagine a radiologist, and that's also I guess when I was doing my master's, that was also the motivation for a lot of things. So a radiologist is technically just swamped with images and calls all day. So we would like to have a medical VQA system step in as a second radiologist, really, that can answer queries and ease the burden of the radiologist. The same goes for pathologists, clinicians. So we're basically looking at VQA as you could think of it as a knowledgeable assistant, really. And the questions can be yes or no questions, and they can also be more complex. So it depends on the data set, the task at hand. But that's essentially the preface or the premise of the discussion that we're going to have. So I think a question that's worth asking really is why multimodal? And so multimodal basically refers to the combination of multiple types or sources of data, right? So in the realm of medical VQA, this means that we aren't just looking at images, we are integrating a variety of data to form a more comprehensive understanding. And we have like a couple of core components for any medical VQA pipeline. And this would be your primary data sources would often then be textual, such as your medical notes or a patient's history. These could be visual, such as radiographs or MRIs or CT scans. I think those would be in radiographs. And this could also be tabular. And for tabular components, we would have like vitals or lab results. And why exactly do go with the multimodal route, right? So I think it's always important to ask the basic questions at the beginning. So the first thing is that it provides a richer context. So imagine that you're trying to decipher just alone from an X-ray image what the patient's illness is, versus having all of their medical history, all of their records, their complaints, as well as your X-ray. So the latter, obviously, I think paints a much clearer picture. And this leads to the next benefit, right, which is enhanced accuracy. So if you use multiple data types, your AI predictions become more precise and of course also become more reliable. And lastly, I guess the approach also offers flexibility because as new data sources emerge, then we can sort of integrate them into our VQA pipelines. And we have like multiple applications of medical VQA, and I've listed a few of them here, but primarily this can act as a tool that aids medical doctors in reaching a diagnosis, right? So this is or can be a crucial ally for clinicians because it can help them identify abnormalities in medical images. Radiologists can greatly benefit. I think that was probably the biggest motivation I believe in developing these systems. is in cancer treatments and cancer diagnoses, so that we help radiologists, and VQA, or medical VQA rather, offers second opinions on the image analysis from radiologists. But I think the benefits or the advantages really don't stop there. So it can go beyond diagnosis. It can act as sort of like a learning platform, and it can sort of act as an interactive and engaging learning tool for residents and your students. And I do believe that I do remember that when I was doing my own master's, because I didn't come from a medical background, it was extremely difficult sometimes to remember all of this anatomy, details. So I think it does help to, it does offer a really nice, engaging learning experience. And this leads then to monitoring. So if you have a good, reliable medical VQA pipeline, then you can track disease progression, you can track treatment effectiveness by analyzing really the changes in your images. So we have currently two, I guess, approaches in which we do medical VQA. One of them is caption-aware VQA, and the other one is parallel multi-head attention. And I'd like to briefly touch upon both of them. And I think I'd also like to quickly mention that these are not an either-or approach, right? So the purposes of each of them would be very different, but these are some of the ways in which we are currently doing medical VQA. So the first one would be your caption-aware VQA. And I guess, as the name suggests, at its core, this is about integrating captions or textual descriptions in your associated with your medical images into your VQA models. So once again, let's think of an X-ray that comes with like a caption, right, or a brief description. So this technique, what we're trying to do here is that we are using image features, and then we're also using the caption in the VQA system to answer your any questions that you might have. And the significance really of this is that if you're looking at a medical image without any prior knowledge, it might be very difficult to discern, right, the key features. So captions can play an important role here, because they can act as a bridge between your images and their high level meaning. And we have like, once again, we have various benefits of this approach. So the inclusion of captions, it can offer a multifold advantage. I believe there's a chat here. Okay, so this is from James. So inclusion of captions, this can offer a multifold advantage because you'll have enhanced contextual understanding. So an image on its own can be ambiguous and unclear, but if you have captions, then that can clarify doubts. And next, I think one of the things that I find really interesting about this is efficiency. So images, especially medical images, can be very difficult and tedious to annotate, and of course, then very expensive as well. So this, with the caption process, I guess that process also becomes quicker and more streamlined. And a lot of the publicly available data sets for medical VQA, they use some sort of automated caption generation to sort of, I guess, annotate the images. And then, of course, we have the advantage of accuracy boost, because we are, we are adding another component in. So the implementation, once again, it's just that for textual data, we'll have LSTMs or transformers. For images, we'll have CNNs, and then we'll merge the information at the end. So I've drawn this very basic schematic, right, of how this will work, but basically have this abdomen MRI here. And you'd, of course, feed this to your VQA model, but then you'd also feed this to a caption model that would generate captions. And you'd feed those captions also then to your VQA model, as well as the image. And this will sort of give you a deeper understanding into the image itself. And then you can have a question and you can answer the question. Next up, we have the parallel multi-head attention. Once again, this is not an either or with the previous approach. This is really one of the ways, I guess, in which medical VQA systems are implemented. So parallel multi-head attention is a bit of a mouthful, but I'll try to, I guess, simplify it. But basically, this is really an evolved attention mechanism, right? So I guess all of us in the AI space know about attention. It was introduced in 2017. It's changed everything since then. But basically, traditional attention, it lets your model focus on specific parts of the data. So you could think of this as a magnifying glass, really, where your attention heads are basically working simultaneously, and each of them is highlighting different aspects or features of your data. And once again, we have three key components of this approach. The first one is your attention heads. So each of your heads would be looking at different parts or features of your textual and visual data. And then there's the component of parallel processing. So they don't, these attention heads don't really wait their turn. They're working in parallel. And at the end, we're merging everything through a weighted fusion. And there are different algorithms for doing this. You could just do an element-wise multiplication as well. That's like the simplest, I guess. And you could have like a weighted attention at the end. So something that sort of combines everything together. So what are some of the key advantages? The first one is granularity, right? So if you have multiple heads that are focusing on different features, you can capture very nuanced details from the medical images and the accompanying text. And then as well, you have efficiency, right? So your heads are working in parallel, so you are expediting the overall processing of the system. And you have an element of robustness also, because you're not just relying on one part of the image, right? So it's looking everywhere, and you're fusing everything together. Yeah, so this is interesting because this now I'd like to, I guess, touch upon the medical VQA datasets. We have 8 publicly available datasets. So the first one, the first that was like publicly made available was VQA Med 2018. And then you have variants of the VQA Med. So then it was released in 2019, 2021, and 2020, and 2021. And then you have 4 others. You have VQA Rad with Style, Path VQA, and Slate. So the concept of all of them is similar, but the questions they ask and the way the questions have been generated, they're very different. And I'd like to, I guess I'd briefly touch upon the ones that I found the most interesting. So I'd like to start with VQA Med 2018 because it is the first one, and it's the I guess it's the base one for 3 subsequent ones that came later on. So the VQA Med 2018, this used a combination of so basically how they generated captions or question answer pairs was through a rule-based algorithm, and then they had 2 human experts to curate the question answer pairs, and they basically emphasized that the question answer pairs should be semantically accurate as well as clinically accurate. And then the next one that I find very interesting is VQA Rad, because this is, of course, we're now shifting to radiology. This was also released in 2018. And but the way this was gathered was different. So the first one, you've synthetically generated the question answer pairs, and then you have human annotators, right, that have come in and sort of verified everything. But with this data set, they gathered real world questions from clinicians about various medical images. And then they basically, and the template was free form. And so they then sought to categorize these questions, right, for the particular data set. Then we have Rad with Style. So this is more intricate because this introduced the concept of visual dialogue in radiology. What this means is that you don't just have one-off questions, right, about, for example, what do you see in this image, or what's the location of this organ, but you have a sequence of questions pertaining to the same image, and the idea is that you want to imitate how you would how a patient would basically interact with the doctor, right? So that was the idea. So that, but then that also makes the task more difficult because your questions are more intricate and more detailed. And path VQA, this was for pathology. So this was, I guess, has those images, and this was also the captions were sourced from multiple places. So I guess, yeah. So I've added like a table, and the just to, I guess, give a brief comparison of the top 3 that are mostly referenced. Of course, the VQA Med 2019, 2020, and 2021, they're also used, but this is, since this is the base one. You can see that for VQA RAD, you have like a bunch of different questions, and so the way you evaluate these models depends on the question category, right? So if you have simple questions such as a yes or no, or a location question, or a modality or organ system question, this is then a classification problem, right? And you can evaluate your VQA based on the evaluation metrics that you would use in a classification task, such as accuracy or F1 score, or any of those. But if you have something that's that deals with text generation. So for example, if your question pertains to abnormality, for example, if you're asking your VQA system, here's an image, what is the abnormality in this image, then that's not really a classification problem, that's a text generation problem. And there's a component of reasoning involved. And then your evaluation metrics would just change to what they would be for an NLP task, right? So any form of semantic similarity in any of those scores might be more relevant. So that's how, there are different tasks for medical VQA based on the questions that you're asking. And so once again, we saw in the previous slide that for VQA Med, you have very simple questions such as location, yes or no questions. But with VQA RAD, there are quite a few. And here I've just attached some images. So for example, for VQA Med 2018, you have this the example question of what does the CD scan of the thorax show? So this is a finding question. The second question on the right is just a yes or no question. But with VQA RAD, you have different questions such as what is the organ system, what is the position of this, what is the location, and that's the way the data set is structured. So which data set you use then depends on what exactly is the problem that you're trying to solve. And then, of course, your evaluation metrics would also change accordingly. And I think I have like a couple of minutes, so I'll try to wrap this up quickly. So basically, we have like 2 different approaches. The baseline approach is you have an image encoder. You have, I think I've added this image, so this should be easier. So you have your image, and then you have some way in which you would extract features from this image, right? So we call this an image encoder. And the typical choices include ResNet, VGGNet. You could also use, I guess, visual transformers. I haven't really seen a lot of that in research. And then you have your question encoder. And here you'd have any sort of recurrent network or an LLM or a transformer to encode the textual information. And this, as this orange block suggests, once you've had your features from both of these blocks, then you sort of want to concatenate them. And typical choices include, some sort of element-wise multiplication, a pooling operation, or some attention mechanism. You just want to combine the features from both of these modules. So you can do this in whatever way. And then once again, based on the task that you're doing, based on your questions, you could either have a classifier or a generator. Typically have a deep neural network here, and at the end you'd for example, so we had this question, what is the CD scan of the thorax show? At the end we have the answer. bilateral multiple pulmonary nodules. So that's typically the way in which most of the systems or most of the frameworks in the medical VQA community work. But then there's also an alternative approach, which we completely take out question encoder. We swap it, we only have the image encoder. And the idea behind this is that if the answers are simple, if the questions are simple, so if you have only yes or no questions, or if you have abnormality questions, then you just rely on image features, I guess. So the authors found out that it's not really important to have a question encoder for those purposes. But mostly we also have, for most of the frameworks in the research community, we do have the question encoder component. And so this is over the years, I guess, and for different data sets, what have been the networks that we've used as image encoders, and what have been the networks that we've used as language encoders? So you can see that VGG seems to be the most popular choice for the image encoders. But for language encoders, we started off very, very strongly with LSTMs back in 2018. But then over time, you jump to 2020, you just see it's mostly transformers. For the VQA Med 2021, you have sort of like LSTMs transformers, but then you can also see that we have the none portion quite a bit. It's like quite big as well, and that basically is for this particular approach where you just have the image only encoder. We are not using the question encoder in those cases. Finally, if I still have some time, I think I'd quickly like to wrap this up with some challenges that we're currently facing here. I think the biggest challenge comes with the scarcity of large-scale label datasets. So I showed a table. We simply do not have enough number of images. We also do not have enough number of question-answer pairs. It's extremely it's time-consuming. It's expensive. And considering the nature of medical data, curating and annotating vast amounts of question answer pairs is it requires expertise. It's time intensive, and of course then it's also expensive. And we also then face the challenge of designing goal oriented VQA systems, right? So we saw that these systems, they need to be tailored for specific tasks within the question within the medical domain. So for different questions, we'll have like different metrics to evaluate the system. And next up, we have clinical questions can be very diverse, right? So clinicians can ask, since they need a deep understanding of the problem, they can ask a very diverse set of questions. So it's once again, it's difficult to curate these data sets because what's the limit on the number of questions you can ask, right? So and finally, I guess when we're combining multiple modalities, then there is the challenge of fine-tuning these models or tuning them from scratch, and then so tweaking and modifying those parameters does remain a challenge. And I think, yeah, so I've added this QR code here. So if you want to take a picture for resources, you can do that. I've also added the slides there. But yeah, that's pretty much it. And that brings us to the end of the session. I'm a minute, there's still a minute to go.
No,
But,
no worries.
yeah.
Do you mind going back to the previous slide, the QR code?
Yeah, sure.
I'll take one. Sweet. If there are any question from the audience, yeah, good luck to feel free to put them in the chat. So clap from Adrian.
Okay. Sorry, James, can I ask you a question?
Yes, please.
Okay. Yeah, so thanks for sharing your work. So do we know roughly the contribution of the different data sources? Like if images contribute for 70% of the result, or is it text? Like, do we have any like sort of feature importance?
Yeah, I think so. Images do contribute most of the most of the information, because we did see. So if I can just go back up to this slide, we did see that so most of the modalities do have a question encoder where you are encoding information from the text part. But then from 2019 onwards, you have like a slice, and that has gotten bigger, right? Of not having any question encoder. So images or image encoders or image features are the primary sources of information. But then you also have the language information or the text information from the text encoders. But we do see that there is a trend of moving away also from them. And surprisingly, these frameworks that do not use any language encoders work quite well. So they were actually very successful, had good results. So to answer your question, I do not have like a percentage that I can quote, but most of the information comes from the image features.
Okay. Yeah, it makes, well, actually it's quite interesting, because it almost like we were multimodal and now they're moving back to only images. So yeah, I'm curious how, because like it's such an important field, and I feel that because of the privacy and how like healthcare, it seems like a sector like finance is always lagging behind like the current technology. It would be such a massive contribution for society, having this technology available as soon as possible in our hospital.
Absolutely. No, I completely agree with that. Yes. But I think I don't think we're moving away from multimodal anytime soon. I think that's in the beginning I mentioned the caption aware VQA systems. I mean, you do have if you inject captions also in your VQA system, then your accuracy and reliability increases. For these particular I guess charts that do not have a language encoder, the context then also is that the questions are more simplistic. So I guess that's something to keep in perspective.
Okay, yeah, makes sense.
Yeah.
Thank you.
I mean, in this slide, it looks like unlike the dominance of transformer in language, it looks like for medical image, they still rely a lot on the traditional convolutional neural network-based architecture, right? Like VGG and ResNet, instead of using vision transformer, right? So why do you think, what are the unique attribute of medical images that prevent, like vision transformer from taking over?
Yeah, so yes, from most of the the literature review that I've done, this seems to be the trend. We do rely mostly on traditional systems. I think this could be due to multiple reasons, but one of the reasons that I can think of, especially in terms of if you see the first 4 charts for the image encoders, you do not see, I at least do not see vision transformers. And one of the reasons could be the transformers need a large amount of data, right, to fine tune or to train their data hungry structures. VGG or ResNets or convolutional neural networks, they work really well, even if you do not have like a lot of data, you have like medium sized data. And for all of these 8 publicly available data sets, I think the biggest one has 5,000 images in it, or 10,000 images in it. So that's nowhere near enough for a vision transformer. Of course, with there are more question answer pairs, so we can get away with using transformers for the language encoding part. but at least for the image encoding, we I guess that the biggest bottleneck would be your data.
See. So that sounds like a problem with like the lack of academic benchmark, right, for medical VQA domain. So yeah, our curiosity, and this question a bit self-serving, but like since well, a lot of what we do at Twala focus on the video understanding domain, do you think that we progress in terms of utilizing the video modality to improve medical VQA system, and if so, like how does that going to be different from using images?
I'd say not very different, because so it depends on you know, if you just have like a video of, you know, let's suppose you know, you have a set of doctors that have performed a treatment, and there's that video, then that video essentially is a bunch of images, right? So I haven't really seen a lot of video modality in the medical VQA frameworks that I've seen. But I guess you'd approach it, you know, the preliminary approach would be similar to just, you know, treat the video as a bunch of images. But I haven't really seen that. But I guess there's also the number of papers coming up would be far less than, for example, for a traditional VQA system, because of the lack of data, really. So then with video data, I guess there's such a sparsity of image data. I'm not sure how much in what I guess quantity we have the video data available. So I've not really seen much of that, but I guess the way you'd approach it would be very similar to the way you'd approach images.
I see. Yeah. Well, why do you think there's such a sparsity of medical data? Like, is that because of?
So yeah, so there's multiple reasons, right? So privacy concerns, ethical regulations, it's difficult to collect medical images, but then also annotating them, right? So for just normal images, it's much easier to annotate them. But for medical images, the annotation it's not straightforward, because you need some sort of experts to sort of be there to verify your annotations. You can't just say there's a tumor here from a bunch of human annotators. You need some sort of you know, clinicians or radiologists to also be looking at the images and verify. So there's a lot of steps, I guess, in the annotation process itself that just sort of limit the amount of data that can be created. So I guess those are some of the obvious ones that stand out.
Yeah,
to explain the sparsity.
Yeah, that will make a lot of sense, and it sounds like that necessity of domain expertise really hinder the process of, you know.
Yeah, I feel like I feel on the annotation part, I slightly disagree on that, because I think it's the role of the doctor to interpret and to like annotate for us the medical record. So I think the data is there. It's simply that I think in general, like healthcare everywhere around the world is doing a terrible job when it comes to systematically collect data, and so it's a complete mess when it comes to collect. I believe that like if we would be able to collect all the data stored in every single hospital in Europe and in the US, we would probably solve at least 50% of the problem that affect healthcare nowadays.
Yeah.
I agree to that, but then I also disagree. And the reason I disagree is because for this particular domain that we're talking about, the medical VQA domain, you need question answer pairs, right? So for that, you need doctors or clinicians to sort of look at your image. Even if your question answer pairs are synthetically generated, you need them to verify, so for that to be ground truth and for that data set to then be used for this particular domain. But yes, if you just have medical images, then yes, I don't think you need depending on the task, then perhaps you don't need that amount of annotation and that amount of expertise and supervision. But for this particular task, I guess that's the reason we just don't have like a lot of annotation or a lot of
Okay.
huge data sets. Yeah.
Yeah, I was like more thinking about a foundational model just for the medical field. So all the visual data and all the like the annotated information coming from the doctor, just to define the foundation and then building on top of it like specific instruction tuning or chatbot like models, because at that point the model would have already had a rough understanding of the image without any context.
Yeah, I think in that case, then for foundational models, then once again, it's a chicken and egg problem. You need a lot of images. So
Yeah.
maybe we do the what you have suggested, to have like a lot of from the US and the Europe, have like all of those images. So maybe yes, we can build foundation models. We have a lot of images, sure.
Yeah. We actually had a speaker, I think a few weeks ago at RIS. We talked about this topic. So, if you're interested, you can go back to our playlist and watch his talk. Anyway, we 10 minutes over time. So thanks both speaker Minjoon and Tahreem for spending your time today with us, even though they are a completely different time zone. And thanks for Lucas. Looks like majority of you guys stay for this extra 10 minutes. So appreciate your attention and patience. And yeah, we'll send a recording of this probably 2 weeks from now. And looking forward to next session. Actually, Kartik, one of our speakers next session, is currently in Zoom. So looking forward to his talk next week. And enjoy the rest of your weekend, everyone.
Thanks, guys. Have a good weekend.
Thank you,
Bye,
everyone.
everyone.
James.